Good morning, everyone. Welcome to the class of CE3331 Environmental Engineering 2. In our last class, we discussed this problem where you have to calculate the value of the diameter of a pipe or a sphere. These are the so in this problem here, are you following me?
Yes, sir.
Yes, sir.
Um, for a pipe flowing full, for a circular pipe, two things: circular pipe flowing full, R equals to for circular pipe flowing full, R equals to
A by P.
d by 4. Yeah, of course, R equals to a by b for any pipe, for any pipe. But for a circular pipe flowing full, if you put a equal to pi by 4 d square and p equals to pi d, then you get R equals to d by 4. So you can replace R with d by 4, right? D by 4 to the power 2 by 3 and s to the power half. Now q equals to what? Q equals to velocity into area. So we just multiply this. Q equals to velocity into area. Velocity is this multiplied by area. Area equals to, for circular pipe flowing full, pi by 4 d square. So as you can see, Q is given 4 times than the other previous velocity. Here you know the S, only unknown is D, right? So you calculate the value of D. Clear?
Yes, sir.
Okay. Now this Manning's equation, this Manning's equation can be solved. Basically, engineer has developed a scale, this scale, which can be used to solve the Manning's equation. So Manning's equation can be solved. Instead of doing these things, it can be solved using this scale. Same thing. Okay. You see that the capacity or discharge, this is the Q and this is the diameter D, this is the slope S, and this is the velocity. So there is another figure here. It also accounts for the N. Okay, N, coefficient of discharge, N. Sorry, coefficient of uh, friction, N. Then this is the diameter, pipe diameter. This is the discharge Q, and this is the slope. Okay, so let's see. Uh, this graph is for n equals to 0.013, running full. This diagram is for any n, where the n value you can see, you can determine the n value from here. Okay. This graph is also same to the previous graph for n equals to 0.03 running full. Only difference is the unit. You can see this is cubic feet per second and this is liter per minute. That's it. Okay. Now let's see how to calculate the value from here. Okay. What is our Q, guys? 39.4, right? Right.
Yes, sir.
Okay. So let's see. 39.4. What is that? Here is 39.4. Fine. This is 39.4 here. Then we need to calculate d, by the way, right? What is the slope here, guys? 0.005. This is 0.004, 0.005. This one is 0.005. If you know these two values, then you just connect them together. Connect them together. Are you following me?
Yes, sir.
जी सर.
And you extend it further. You extend it further. Okay. Now you look at this line for D, where it has cut this line. What is this value, guys? 33 point something, am I right?
Yes, sir.
And what is the unit? Inch. So D equals to 33 point something inch. Clear?
Yes, sir.
Yes sir.
And velocity is what, guys? 6.3 or 2 something. If you calculate, you'll get the velocity like this. Clear?
Yes, sir.
Yes sir.
Okay. Remember, this graph is for n equals to 0.013. You cannot use this graph for a value equals to 0.015. Okay, you have to use this graph. Did you see here the value changes? How to use this graph, guys? Let's see. uh, for example, we have a problem later, like which we can use maybe. Anyway, no problem. For example, you know your Q, right? For example, your uh, this is slope, right? Okay, fine. If someone tells you that this is the equation, let's do it half. Q equals to what? Q equals to will be 1 by n r to the power 2 by 3 s to the power half and area, right? Q equals to v into area. So basically this is d by 4. For a circular pipe flowing full, A will be 5 by 4 t square. Now, if I tell you that I have a pipe diameter of 400 millimeter, I need a discharge of 0.5 meter cube per second. Are you following me?
Yes, sir.
I have a diameter of 400 millimeter. I need a discharge of 0.5 meter cube per second. I have An equals to 0.015. Now, what would be the slope to generate this discharge with this N and this D? Okay, so you go q, for example, any value. Maybe this is here point zero 0.06. Let's say this is 0.06. Okay, and your d is maybe here around 250 millimeter. Let's say this is 250, and your n is around 0.0114, right? 0.014. Let's say this is 0.014. So what you do is, first of all, you click the diameter here. Okay, and you use the q here, and then you connect them and extend them up to the turning line, up to the turning line. Now here you need to change your direction based on n. What is your n? Your n is 0.014 here. So rather than going this direction, you will move your direction based on your n. Are you following me?
Yes, sir.
If your
Yes,
n
sir.
is 0.02, you will be here. If your n equals to 0.006, you will be here. If your n equals to 0.01, you will be here. If your n equals to 0.02, you will be here. Okay, in this case your n equals to 0.014, so you just extend it accordingly, and the point where it cuts the slope, this is the required slope, around 0.0085, and your velocity will be this. Clear?
Yes, sir.
Okay, now one important thing, look, this graph, this diagram, all are for a pipe which is circular and flowing fully. Now, in a sewer, as I told you, the flow is not uniform throughout the day, right? In the morning, the demand is high. In the late night, the demand is much lower. Am I right?
Yes, sir.
Yes, sir.
So you'll see that when you are here, the water level may be air. Then when you are at the peak in the morning, this is in the midnight. In the morning you're at peak, so this may be here. The water level is here, right? Right.
Yes, sir.
Now you see that majority of the time the water is not flowing full. This is only once in a day. On the other time of the day, the water level is either here, or there. That means this is not full. This is partially full. So partially full. Partially full. So for this partially full, that means the water level is here. For this partially full pipe or sewer, you cannot directly use this equation. You cannot directly use this equation. Okay? What do you have to do? Basically, look at this pipe. Water level is here, partially full. So this is theta. Okay, this is the partial depth. This is the full depth. Am I right? Full diameter. Can you hear me?
Yes, sir.
This is capital D is the full depth, and the small d is the partial depth. Like this is a small d, and this is capital D. So your weighted perimeter now, instead of this whole pipe, your weighted perimeter is only this, right? This is weighted perimeter. All right. Hmm? Am I right?
Yes, sir. Yes, sir.
So, and you have to convert. Look, you have to convert all of the values here. Theta, d, these things. So these computations are laborious. That means it is time consuming, difficult. Okay. Therefore, a diagram known as hydraulic element diagram has been formed. This is the hydraulic element diagram. I'll tell you how to use this. This is a sphere when this is partial, when this is flowing full. This is the same sphere when this is flowing partially. So in flowing full, and this is partial. Here the velocity is v, here the discharge is q, here the depth is d, right?
Yes, sir.
And in partial velocity, a partial flow, small v, small q, small q. This is partial velocity, this is partial velocity, this is partial depth, this is partial flow. Full velocity, full discharge, full depth. Clear?
Yes, sir.
Now you can make this small v by capital V, small q by capital Q, small d by capital D. Can you do that?
Yes, sir.
Now this graph is based on these ratios of hydraulic elements. Okay, the perimeter here is the whole perimeter. So this is a p. Okay, and here it will be, sorry, it is flowing full, so a full, and this is here is a partial, so a full divided by a partial. Instead of a small q, we could have also write q partial divided by q full. Velocity partial here, velocity full here. Clear, guys?
Yes, sir.
Now look at this figure. Here we have put the values of these ratios. Okay, and here this is the ratio of flow depth to the diameter. That means d by d, d by d. And this diagram is for weighted perimeter. That means area partial divided by area full. What does that mean? Area partial is this, and area full is this. Are you following me, guys?
Yes, sir.
Sorry, this is for this area. Okay, area. This is area partial divided by area full. This is a weighted perimeter. So P partial divided by P full. Discharge. Q partial divided by Q full. Or a small q by capital Q. Same thing. Okay. Velocity same. Hydraulic radius same. Several important points can be observed from the hydraulic element diagram. Velocities under full flow conditions and half flow conditions are equal. Look at this. Here, when you have half flow condition, that means d by d equals to 0.5. Then look at the velocity. This is 1. Did you see? That means when d by d equals to 0.5, then v partial divided by v flow, or small v by capital V equals to 1. That means small v equals to capital V. That means the velocity, when the depth is this, partial depth is 50% of the full depth, then the velocity is equal. Partial velocity is equal to the full flow velocity. Did I make it clear?
Yes, sir.
Okay. Now look at this. When the velocity is maximum, at this point is maximum. Here, right? The rightmost maximum. And for what point? 0.8. And more than 1.2. You see, this is more than 1.2. That means when your small v by capital V is 0.8, then your small v by capital V equals to 1.2, and your small v is 1.2 into V. I think which one is larger? Is partial flow velocity or full flow velocity? Which one is larger? Tell me.
Full, full. Full, sir.
This one is larger, right?
Yes, sir.
Now you can imagine when the flow small d is around 80% here, then you get the highest velocity instead of the full flow velocity. Why? Because when there is full flow velocity, there is also friction right here, because the water will be in contact with the surface of the pipe. There, so there will be friction, and that friction actually reduces the velocity to some extent. That's why here we have the highest velocity. Did I make it clear?
Yes, sir.
Okay. That means maximum flow does not occur at full depth due to frictional loss. Does not occur at full depth. Okay. Maximum flow occurs when when d by d equals to 94%, and this is 1.07. This is q. Where is q? This is the q. Maximum point is here, and this is around, if we could go, this is around 1.07, and this is what go there, 0.94, right? So maximum flow occurs when d by d equals to 0.94. Again, this is d by d, d by d. Is it clear?
Yes, sir.
Now, how to calculate or apply this diagram in the estimation of hydraulic parameters? The first step is to determine the area, velocity, or discharge for the sphere flowing full, and also the ratio of the depth of flow to the diameter of the sphere. And in the second step, the necessary multiplier for the partial flow sphere is then read from the diagram. Let's see an example. This is an example problem. A circular sphere has a diameter of 30 centimeter with n equals to 0.013, slope equals to 0.004. So let's q equals to 1 by n r2 by 2 by 3 is to the power half into area, where r equals to d by 4, d equals to pi by 4, d square. Now what is given? A circular sphere has a diameter of 30 centimeters. That means d is given. D is given. N is given 0.013. N is given. Slope is given. Slope is also given. Determine the rate of discharge and discharge velocity for full flow condition and depth of flow equal to 7.5 centimeter. So for full flow condition, you just apply many this formula. This is for what, guys? This is for what? R equals to d by for which condition?
Sir, full condition.
Full condition. A is pi by 4 d square for which condition? Full flow
Full
condition.
condition.
Okay,
Full.
so A for full flow condition, we can determine this. So n, the value of n equals to 0.013. The value of d equals to, remember you are using this equation, that means everything has to be in SI, meter. D equals to 30 centimeters, that means 0.3 meter. And what else? ds, s is what? S is unitless, so
Sir, 0.004.
0.004. So calculate the value, please. Q. Please calculate the value of Q. What was the value, guys? What was the value, guys?
স্যার আমার তো আসছে 0.26।
0.26. Did everyone get the same value? Meter cube per second, right? Did everyone get the same value?
These are 0.061.
0.061. What else? Anything else? So discharge equals to this liter per minute, right? We have calculated in meter cube per second. So 3570 divided by 60,000. Okay, and tell me what is the value for liter to meter cube, 1000 division, and from minute to second, 60. Tell me the value, please.
স্যার এটা করলে স্যার আসে 0.059।
So 0.06 something, right?
জি স্যার।
জি স্যার।
So this is the correct value actually, 1061 meter cube per second. Okay. Now this is the condition flowing full, which is actually what? You can put any unit because they didn't ask for the unit, so you can use any unit. Okay, no problem. So remember the full discharge and discharge velocity. So you can calculate the velocity. V equals to Q by area, where area equals to this, right? Tell me the value, please. 0.061 divided by this. Area equals to this. I go for ds cube. Area equals to 5 by 4.3 square. Tell me the value, please.
0.848.
0.86.
স্যার 0.86।
So 0.061, 0.061, 061 divided by 108, right?
জি স্যার, 0.86।
স্যার
7 or 8. That is clear, right?
স্যার
0.78.
স্যার ভেলোসিটি আছে স্যার 0.86।
No, 0.078 meter per second. Who got this value? Tell me. Who got this value?
স্যার আমি তো 0.84 বললাম স্যার।
0.84.
0.84.
Okay, so then I heard it wrong. Sorry. This is 0.86 or 0.84. Let's say this is 0.85 meter per second. Clear?
ইয়েস স্যার।
So this is the velocity and discharge in full flow condition. You must remember this is, you must have to remember that this is full flow condition. Full flow. Okay. Now they have been asking for discharge and velocity when the depth of flow is equal to 7.5 centimeter only. That means this is your pipe. What is the diameter, guys? 30 centimeter, right? And they are asking
Yes, sir.
when the depth is 7.5 centimeter only. Here, 7.5 centimeter only. Then what will be the discharge? Then what will be the velocity. So small d is what? 7.5.
7.5.
Capital D is what?
30 centimeter,
30.
0.3 meter.
So d by d is what, guys? D by d is what? Everyone bring out
Zero
their
point 0.2, sir. 0.25.
everyone bring out your calculator, please. In this class, I want you everyone to take your calculator and determine the parameters that we are solving together. Okay, everyone do it. That will help you to get prepared for your exam. So d by d goes to 0.25. Now, what is that small q? What is the small velocity? Let's call it a small q and small velocity. Partial flow and partial velocity. For this, first of all, you need to know the full flow discharge and full flow velocity. You need to know this. Okay, and then what do you do is you calculate d by d. Step number 1, you need to calculate the full flow parameters. Step number 2, you have to calculate d by d. We have done this here. Now we are doing this d by d equals to 0.25. Now step number 3 is you need to go to the partial flow diagram. You need to go to the partial flow diagram. Go there. Now look at this. What is your d by d, guys? 0.25, right? Let's look at 0.25. Why is 0.25? 0.2 and 0.3. So 0.25 will be here. Am I right?
Sir,
Check this. Change the color. This is 0.25. Now what do you need to know? You need to know the discharge, right? So let's see. The discharge, where is discharge? This is the discharge graph, right?
Yes, sir.
Don't get confused. This is the discharge graph. This and this. Okay. So here, they are cutting it here. At this point, this is cutting, right? Now tell me what's the value? 0.1, 0.2, that means 0.14 or 0.13, am I right?
4.14.
0.14, yeah. So your discharge by and then this graph is what? Small q by capital Q, right? Small q by capital Q. That means the value of small q by capital Q is what? 0.14 or 0.1. They have taken 0.12. That's fine, no problem. 0.12. Clear?
Yes, sir.
Now it's easy. You know capital Q, you calculate small q. So small q equals to full flow velocity into 0.12, which is full flow velocity was what? 0.061. 0.061 multiplied by 0.1. Whatever the value is, meter per second. Then make it clear. Similarly, you need to know what? Small v by capital V from this figure. Let's look at this. Where is the velocity one? This one is the velocity. Right? But that is cut place here. And this one. And this is around 0.71, right?
Yes, sir.
So small v by capital V. This is around 0.71. I think they take 0.65. Let me check it again. D by D equals to 0.25. 0.25. They're taking it as 0.65. 0.65 in any way. The velocity. I think they are wrong. We need to take it 0.71. Okay, this is the velocity graph. This, and they are cutting it here. So it should be 0.71. Okay, so it is 0.71 or 0.72, whatever you say. And small v equals to capital V into 0.71 equals, what is the capital V, guys? 0.85. 0.85 multiplied by 0.71 meter per second. Clear?
Yes, sir.
So that's how you determine this. You could have also used this nomograph to calculate the values, but you have to use the partial flow diagram also, right? Oh, they are using this graph. Maybe this is, that's why 0.25 and 0.65. Anyway, so I'll give you the nomograph in the exam, so that would be not a problem. So another problem, practice problem, that is an 18-inch square with n equals to z 0.013 is laid on a slope of 0.015. It means this is the square, and d equals to the d 18 inch, n equals to 0.013, slope equals to 0.015, slope equals to 0.015. What is the capacity when flowing half full? What is the capacity when flowing half full? What do you have to do, guys? First of all, you need to calculate the full flow Q and full flow velocity. Clear? Right? Step number 1. Step number 2, you have to calculate d by d. Half full means what? 0.5. Clear?
Yes, sir.
And then you go to the partial flow diagram. You calculate, you determine Q by Q value, and you determine small v by capital V value, and then you calculate it. Small Q, small v. Okay. What will be the velocity when the depth of flow is 4.5 inch? Again, you calculate d by d. D is 4.5. Capital D is what? 18. Clear? Clear?
Yes, sir.
Okay. So this problem can come in many forms, like I can tell you that a sphere has been uh, designed to have a flow of 0.5 meter per second. That is the capacity, full flow condition. Okay. Now we got the diameter for this is like 400, I don't know, millimeter. Okay. But after designing the sewer network, you found that in the market 400 millimeter diameter pipe is not available. You have 450 millimeter diameter pipe. Are you following me?
Yes, sir.
So you gave 450 millimeter. Now the question is, this sphere will never be in full flow. Why? Because now the diameter has been increased. 0.5 will be always less than the full flow. 0.5 was full flow for D equals to 400 millimeter. But now your D has been enlarged, 450 millimeter. So 0.5 will never reach the peak. Am I right?
Yes, sir.
So the question can be under this, tell me what will be the velocity. So what do you have to do, guys, in this case? You have to calculate the partial flow velocity, right? Right?
जी
Yes,
सर.
sir.
Okay. So go back to the step again. Step number 1, calculate the full flow velocity. Now remember, your pipe diameter is 450 millimeter. So your full flow velocity 0.5 is 0.5 your full flow velocity. Is 0.5 your full flow velocity.
Yes, sir.
0.5 is here. How does it become full flow velocity?
Partial, sir.
Partial sir, full flow na.
So what will be the full flow velocity? Q 1 by n r to the power 2 by 3 s to the power half a. You need to know the diameter. Do you know the diameter?
Yes, sir. 18 inch.
18 inch. Where did you get this from? This is the diameter, 450 millimeters,
Sorry.
right? N, let's say n is given, 1 by n. R, that will d by 4. S, let's say S is also given. Can you calculate Q?
Yes, sir.
You can also calculate small, capital P. So capital Q, capital D. Next step, small d by capital D. But here you don't know small d by capital D. Do you know that? You don't know that, right? I
Yes,
asked you
sir.
to calculate what? I asked you to calculate small v. The question is, do you need to know small v by capital D? No. Look at this figure. You know what? You know capital Q, right? Right?
Yes, sir.
जी सर.
Okay. You know small q, right? What is small q? 0.5. Let's say capital Q is 0.7. Then you know small q by capital Q, am I right?
Yes, sir.
Fine. What is the small q? This is the graph, this church. Let's say, tell me the value, 0.5 by 0.7. What's the value there? 0.71, right?
जी सर 0.71.
So let's say 0.71 here. This church graph is this 0.71 here. Did you see it has already cut the velocity diagram?
जी सर.
Where, by the way? Ah, yeah, look at this. For a particular depth, uh, where it has cut the, this is this church.
0.9 হবে.
Look at this, 0.7 for this church, right? What was the value? 0.71, for example. So 0.71 we got here, right? Now we take a horizontal line. Did you see? We take a horizontal line from this point. This is your small d by capital D. Clear?
Yes, sir.
Here, you did not know small q by capital Q. You knew small d by d, and from this you calculated this. Now you already know small q by capital Q. So from there you can calculate small d by capital Q. The reverse. Did I make it clear?
Yes, sir.
And for this horizontal line, did see where it cuts the velocity graph here. Here. This is basically 1.07 maybe. So small v by capital V equals to 1.07. Small capital V, you know. So small v, you'll be able to calculate, right? Clear?
Yes, sir.
That means you can check this small v with the minimum velocity, self-cleansing velocity, remember? Around 2 feet per second. V, self-cleansing velocity, remember that? And your small v has to be greater than or equal, right? Right.
Yes, sir.
Otherwise, it will not be able to clean the debris. Now, if you found that your small v from here is 1 feet per second, can you use 450 millimeter diameter pipe? Hmm? Your velocity is less than the minimum velocity. Would there be washing, cleaning
No,
of
sir.
the solid? No. So then can you use 450 millimeter diameter pipe? Hmm? You cannot, because if you use 450 millimeter diameter pipe, your smaller v at the actual velocity will be less than that 2 feet per second. If this is less than self-cleansing velocity, CLF self-cleansing, then it is not acceptable. This is acceptable. So that means you cannot use 450 millimeter diameter pipe. Clear?
Yes, sir.
Yes, sir.
You have to change the pipe, or this is the equation: v equals to 1 by n r to the power 2 by 3 s to the power half. To increase the velocity, you have to increase the slope. You can give a steeper slope to increase the velocity, maybe, or you have to reduce n to increase the velocity, right?
Yes, sir.
Sometimes I may ask you that if I, instead of 400, if I use 450 millimeter diameter pipe, then what would be the new depth? What will be the depth of flow? What is the depth of flow? That means you have to calculate small d by capital D. As I told you, you know small q by capital Q. So from this small q by capital Q, we can calculate small d by capital D. What is the value from here? 0.65 approximately, right? So small d by capital D will be 0.65. What is the capital D here? It's given here, 450, right? Capital D is 450. Clear?
Yes, sir.
Remember, we are doing it for the analyzing for the new pipe diameter. This is 450. So don't use 400 here. Okay. Any question?
No, sir.
Okay. What I have just told you is that I'm repeating again. Swear you have designed it. Your cube is 0.5, and you have designed the sphere 400 millimeter diameter meter cube per second. That means at least once in a day there will be full flow, right?
जी sir.
So instead of this, if you use d equals to 450 millimeter, then with the same slope, can you ever reach the top with 0.5? 0.5 was 400 millimeter. Now with 450, would 0.5 reach at the top? Never, right? It will be below the top. Am I right?
Yes, sir.
So if I ask you, what is the new velocity? Check if this is greater than or equal self-cleansing velocity. Simple. You need to calculate the Q for this pipe or this pipe. This pipe. For this pipe, capital Q is 0.5. But for this pipe, small q is 0.5. Capital Q is unknown. So you calculate this Q equals to 1 by n r to the power 2 by 3 s to the power half into area. D you know 450. S you know. You calculate. You calculated capital Q. You know a small q, so you calculate small q by capital Q. Now go back to the figure. This charge of this, you put a horizontal line. You know everything. You know small d by d. You know small v by capital V. You know small d by d. You know small v by capital V. Clear? Now, if you want to calculate a small v, you have to multiply capital V with the number that you get from the figure. What is the capital V? Calculate from here, from Q. Clear?
Yes, sir.
You want to know the depth here? Calculate the depth from here. Easy. Okay. So that's it. Any question?
No, sir.
Okay, guys. Thank you very much. Have a good one and stay safe.